Thanks, Nick. So it's great to be here today and be able to talk to you about algorithms and computing. Now, the word algorithm has entered the vernacular. Most people have heard it, and many people have a pretty good grasp of what it basically means. Whenever I'm talking about algorithms, I try to pick an example that is pertinent to the situation at hand. And so I remember very well, earlier this year, after I had some minor surgery, I found myself in the wake-up room talking to the nurses and explaining to them that the surgeon has just performed an algorithm on me. And that even the nurses were following an algorithm in trying to get me to wake up. Now, I can see two reactions to this story. One is, what a commitment. The other one is, that is really weird. And so, in my defense, I was heavily drugged at the time. But I can also see that this contributes to a rather negative stereotype that is afflicting computer science and computing. So many people remember probably Dennis from Jurassic Park or the Warlock from Die Hard 4. And these pictures indicate somehow that computer science is a dark art, always performed and practiced by some nerdy guys. And while, like all stereotypes, these pictures contain some element of truth, they also indicate that computing and algorithms is not for you if you don't look like these guys. But nothing could be further from the truth. And by the way, my office does not look anything like that. And it's not as if we don't have other examples. So one of the oldest is Ada Lovelace, and I just learned coming here that she lived right next door. I didn't know that before. So Ada was a mathematician, and when in 1837 Charles Babbage introduced his analytical machine, it was Ada who created the first algorithm for it. So Ada is widely recognized to be the first programmer. I think we should be showing more pictures like this one. Now, you could be forgiven thinking that algorithms and computing is all about clever interactions with machine, programming, tweaking, hacking. And in order to illustrate this, let's start looking at a typical workday in your life. It starts in the morning by being waken up by an alarm clock. Well, nowadays, many people use their smartphones for that. But I remember very well the times when I had, in different hotel rooms, figure out how that particular machine was to be programmed so that it woke me up at the right time. Then, in the bathroom, some people may want to listen to their favorite music on a Bluetooth-enabled speaker. And, well, that requires first pairing the devices and programming your playlist. If you take your car to work then, and you have a navigation system, you have to program it so that it is able to find you the best route. Or even if you use public transport, you have to convince a ticket machine to print you the right ticket. And that requires pressing the right buttons in the right order, and otherwise it wouldn't work. Now, and what would we do in all of this without the most precious of machines, namely the smartphone and all the apps on it? But even if we take away the electronic machinery here, the algorithms are still there. It's just that they're performed by different computers. It starts with a mechanical alarm clock in the morning. Or think about ribosomes. These tiny little machines that are working in all of your cells right now, keep you alive and able to follow this talk. A ribosome is basically a computer that executes algorithms that are encoded in your DNA. But then the most powerful computer of all are actually we humans. And think of the second step in the morning, the music in the bathroom, right? Most people actually today, they sing or whistle their favorite tunes. And a music piece is essentially an algorithm that is created by the composer of the music. And then there are many algorithms that are currently only performed by humans. And this morning, I visited the tower, and that was very inspiring. Lots of very interesting algorithms, but I wanted to keep this talk not a scary talk about algorithms, so that's why I stayed with these more mundane examples like binding a tie, making a braid, evacuation procedures, or voting procedures. These are all examples of algorithms. Now, and then taking an example that is pertinent to the situation, we are all here right now participating in the Chatham House event algorithm, and we're currently in the presentation step. Now, to summarize this part, we can see algorithms everywhere, but also we can find them in many cases outside of machines, and they do not need programming or a programming language in order to understand what they are. And that gives us a good opportunity to engage a wide audience and make this subject available to a wide audience. This is similar to learning an instrument and music. You do not have to study staff notation or music theory before you can learn an instrument. And that is basically the approach that I'm following and that I want to apply, namely taking everyday situations and stories to explain concepts of algorithms and computing. So, what then is an algorithm? It's basically a plan or a method to solve a set of related problems where the algorithm consists of a number of steps that are unambiguous and effective. When an algorithm is executed, it takes as input a representation of a problem and transforms it into a solution. And this execution phase is called computation. So taking the tie-binding example, we could say that by executing the tie-binding algorithm, we are computing a piece of clothing from a piece of cloth. Now, in most cases, an algorithm is expressed in some language, in a language that is to be understood by the computer that is supposed to execute the algorithm. And as we've seen in the tie-binding example, this language does not have to be a programming language. It doesn't even have to be a textual language. It can be given by a sequence of pictures in many cases. The fact that an algorithm is expressed in a language allows the separation of the description of the algorithm from its execution. And that enables an algorithm to be performed many times by many different computers, many different places. And if you look around, you can see all the ties here as an evidence of that fact. And finally, an algorithm must be able, or it must be possible to apply an algorithm to different kinds of inputs. After all, you want to bind different ties and not just only one. So there's a number of concepts of algorithms that deserve a closer look and that I want to talk about now. One, or the first question actually that comes up is, how is it actually possible that by manipulating objects or even bits in a computer, an algorithm can solve a problem in the real world? Let's look at this example. Suppose you draw a horizontal line of length 1 inch, and then you draw a vertical line perpendicular to the first, the same length, and then you connect the two open ends. You've created a right triangle, and then you measure the diagonal. Well, what have you done? You have actually computed the square root of 2, or some approximation of it. Now, how does this work? This works because the things and objects that are manipulated by the algorithm do not generally stand for themselves, but they stand for something else. They are representations. In this case, the lines represent numbers, elements of a different domain, in this case, math. I'll give you another example. Many of you know the story of Hansel and Gretel, who were led into the forest and left there by their parents, and they had to find their way back by following a path of pebbles that Hansel had dropped on his way into the forest. Now, by following the pebbles, what they did is they transformed their location, and that worked because the pebbles were a representation. They did not stand for shiny things, but for locations in the forest all the way to their home. And by following the path of pebbles, Hansel and Gretel basically computed their way out of danger to safety. Now, the second question about algorithms is whether or not they are correct. We want algorithms to produce correct results. Incorrect results are not only useless, they can be also outright dangerous. And let's take as an example Hansel and Gretel's pebble following algorithm. Here's a very simple form of it that says, locate the closest pebble until you're home. That sounds easy enough and reasonable. So after the first step, we would expect Hansel and Gretel to be at the first pebble. And after the second step, we expect them to be at the second pebble. But if we look very closely, this is not what happens. When Hansel and Gretel are at the first pebble and the instruction is locate the next pebble or the closest pebble, well, it's right there. It's right there where they are. So in the second step, they should not move at all. They should stay where they are. And the same, actually, in the third and any other steps. So with this algorithm, they cannot make any progress. They're really stuck on the first pebble, and this algorithm does not terminate, and it's thus incorrect. Now you may say, well, this is really nitpicking, right? No rational person would do something like this. But remember, I said at the beginning, an algorithm must consist of operations, of instructions that are unambiguous. And, well, this one is clearly ambiguous. So, but it's not hard to fix this algorithm. We could say something that avoids Hansel and Gretel staying at the same pebble. So, with this changed algorithm, Hansel and Gretel, certainly in the second step, can reach the second pebble. And then in the third step, can reach the third pebble. But wait. Now, it could happen that the first pebble is actually closer to the second pebble than the third pebble is. And that means in the third step, they could actually go back to the first pebble instead of advancing to the third one. And then in the fourth pebble, they're back at the second pebble. And so on and so forth. So basically, they're stuck again, this time in a back and forth loop between the first two pebbles. So this does not have to happen. And it could happen actually between any two pebbles along the path. And there are some cases, actually there's only one case, where this does not happen. But in general, this can happen. And so again, this algorithm does not work. Finally, we can fix this algorithm by saying that Hansel and Gretel should follow the pebbles and not visit any pebble they have visited before. That avoids them from getting stuck. But the moral of the story is, it's not so easy to get algorithms correct. And I mean, there's many, many examples that some of you have probably heard of that illustrate the effects of bugs in software. This ranges from annoying if airlines have to ground their flights because of a glitch in a computer, to very costly, think of the Ariane 5 explosion, or to really dangerous and deadly when patients are administered 100 times the allowable dosage of radiation, and people die because of that. Now, correctness is only one property that we care about with algorithms. The other property is efficiency. An algorithm must be able to complete its work in time so that the result is useful. To study this aspect a little bit more, let's look at the algorithm that is performed by Hansel on his way into the forest when he drops the pebbles. So before we can answer what the runtime of that algorithm is, there's a few observations we have to make. The first is that the runtime of an algorithm is not measured in time. We don't say, oh, the algorithm's runtime is 5 minutes and 2 seconds or something like this. No, the runtime is measured in steps, in abstract algorithmic steps. So in our case, we would say that the effort it takes to go from one pebble position to the next and drop the pebble, we would count this as one step. And that makes sense because, in general, this will be roughly the same for all the pebbles involved. The second observation is that since algorithms have to be applicable to different inputs, we cannot just give one number of steps as the runtime of an algorithm. We have to actually express this as a function of the size of the input. Well, after all, Hansel and Gretel were let in the forest twice. Right? And so these algorithms have probably different runtimes. So with this, we can say that the algorithm for dropping n pebbles takes n steps. This behavior is called linear because the number of steps vary in the same way or proportionally to the size of the input, and that is quite good, and in many cases the best we can hope for. But there are other possibilities. Let's look at a slight variation of this problem, where suppose Hansel does not have pockets to store the pebbles in. And so now to drop each pebble, he has to go all the way back home to fetch the pebble and drop it. Now, what is the runtime of that algorithm? Well, this can be best understood by looking at one particular example pebble. Suppose Hansel wants to drop the fourth pebble. He's back home, picks up the pebble, then has to make 4 steps to drop the pebble. But then the runtime to drop all these 4 pebbles must include, of course, the runtime of the previous 3 pebbles. And so we can see if we sum up all these numbers and then also include the number of steps it always takes to go back, then we come up with n squared steps are required to drop n pebbles. Now, and that is clearly prohibitive. If you read the story, you will find that the parents were already impatient when Hansel was executing his linear algorithm. Right? So this one would have probably not worked at all. I want to use another example to illustrate the dependency of a runtime of an algorithm on the representation that is being chosen. So I assume that many of you know the Indiana Jones movies. Indiana Jones was an archaeology professor, who in his free time is chasing ancient artifacts. And in one of his adventures, he has to cross a deadly abyss by crossing a tile floor that had only some tiles that are safe. And to identify the correct tiles, he had to use a secret code word. Now let's assume, for simplicity, that this tile floor is regular and we have the tiles arranged in a matrix, and that Indiana Jones has to step in each row on one tile corresponding to the letter of the code word. Now, in the movie, if we check out the tile floor, we can see that contains about 50 tiles, a little less than that, and that can be represented by a matrix of 6 rows with 8 tiles each. Now, to appreciate the efficiency of Indiana Jones's algorithm, the first thing we have to observe is that this tile floor of 6 times 8 tiles encodes over 250,000 of possible paths. And now suppose a slight variation of this story or of this problem. Suppose instead of having letters inscribed on the tiles are blank, and Indiana Jones is given a book. And this book contains on each page a path together with a corresponding word. Now, if the pages in the book are not sorted, then knowledge of the secret code word, with that, Indiana Jones has to flip through all the pages, all 260,000, in the worst case, to find the right path across the tile floor. The movie would be long over. So compare this with the remarkable efficiency that Indiana Jones is actually able to cross the tile floor. He can construct his path tile by tile and letter by letter because he can decompose this work into individual single steps. So this shows that this remarkable increase in efficiency can be achieved sometimes by choosing good representations. Now, I hear some of you thinking, saying, few of us have to cross deadly abysses with tile floors and secret code words, right? But many of us use something very similar. A combination lock works on the same principle. It contains a great number of different combinations, and it takes a very long time to go through all of them one by one to find the correct one that opens the lock. But if you know the right combination, you can adjust the dials independently of one another and very quickly open the lock. And there's another application. Some people like to commemorate their friends' names in the form of tattoos. Now, to a computer scientist, this is a waste of precious skin estate. And if your names that you want to remember are sufficiently similar, you can actually look at these 8 names, encode them with fewer letters using this tiling principle, right? So we can encode 8 letters with just 8 names with just 6 letters. Okay. So I also want to, instead of, in addition to correctness and efficiency, I also want to talk about one aspect that concerns the expression of algorithms. How can we actually write down algorithms? And that is recursion. So we can distinguish the operations of an algorithm into 2 kinds. There are those operations that directly manipulate objects and symbols. And then there are those operations that coordinate the work of other operations. This is similar to the workers in a factory. Some workers really manipulate material, build parts and bigger parts. And other supervisors and other workers, they control what the others are doing. And so in the same way, the operations that do the controlling, these are called control structures, and recursion is one very important, very general control structure, and it's also a very important concept in computing in general. Now, in order to get us started, I want all of you who sit closely enough, who can read this algorithm, please execute this algorithm. All right. Great. So all of you who are raising their left hand, you should not be doing this. You should be actually reading the second sentence still. And all of you who are reading the second sentence, you can stop now. Now, what's the problem here? The problem is that the second sentence contains a reference to itself. And if you interpret this strictly, well, you will be reading this forever, right? It's an endless loop here. So this is really troubling, but Well, this is a form of what is called self-reference, and self-reference is mysterious, but it's also intriguing and fascinating, as evidenced by the artwork of M.C. Escher. Now, self-reference is when a description refers to itself, and recursive algorithms do just that. Now, a different form of recursion we can find in self-similarity, and you have that when a picture or an object contains several copies of itself, smaller copies of itself. This is also called the Droste effect after an advertisement in 1902 for Dutch cocoa powder, where this phenomenon was first observed. Now, it seems that self-similarity and self-reference are two completely different phenomena. They have nothing to do with one another. But if we take a computational perspective, they are very much related. Specifically, if you execute a recursive algorithm, then you often end up with self-similar results. I want to illustrate recursive algorithms with one example in a domain that you all know, which is sorting, right? So the books in the library are sorted. When you're playing cards, many people keep their cards sorted. When you issue a Google query, the results are sorted by relevance. Now, a very simple sorting algorithm is selection sort. That works by taking an unsorted pile of cards, say, and you repeatedly pick the smallest card and put it onto a sorted pile. That works reasonably well. It's a simple method. However, it is not very efficient. In the worst case, it's actually a quadratic algorithm, which we have seen is also sometimes not efficient enough to do a job. A better, more efficient sorting algorithm is Mergesort. Mergesort was invented in 1945 by John von Neumann, and it's based on this very simple hypothetical. Suppose you have an unsorted deck of cards. What if somebody somehow magically could give you two sorted subdecks of this deck? How could you take these two sorted subdecks and create a sorted deck? That is actually not so hard. We can look at these two sorted subdecks and repeatedly take the smaller card until they're both merged into one sorted complete deck. Okay? But then how can we obtain these two sorted subdecks? Well, that is not hard either, because it's certainly easy to take a big deck and split it into two parts, and then we can apply the sorting algorithm recursively onto these two subdecks. Now, this works because they are smaller in size, and the recursion will quickly terminate because they get smaller and smaller and smaller and end up with a base case where each deck has only one card, which is trivially sorted. Now, Mergesort is very efficient. Actually, you can prove formally that in the general case, you cannot find and invent a better or faster sorting algorithm. And as you can see, Mergesort is not quite as efficient as a linear algorithm, but it's much faster than selection sort. Now, I do not suggest in your next bridge or poker round to use Mergesort. So the sight of 5 people sitting at a table recursively splitting their decks, this probably leads more to chaos than it's helpful. So another simple algorithm just works fine. But if you have to sort larger amounts of data, Mergesort is, and the difference between Mergesort and selection sort really matters. So suppose you have to sort all the 330 million, the names of the 330 million residents of the United States. With selection sort, using a contemporary computer, this takes 4 days. Mergesort is finished in a fraction of a second. So to understand recursion better, I think it's instructive to compare it with time travel. And in particular, the movie trilogy, Back to the Future, that some of you probably know, provides some interesting parallels and analogies. The first is that time travel is often invoked and used to solve problems. You go back in time to change something in the past so that the ensuing actions lead to a state in the present that then make a problem disappear or easy to solve. That is exactly what we have done with Mergesort. Right? We have recursively sorted two subdecks, and that made it easy to create a sorted complete deck. The second thing we can observe is that in time travel stories and movies, we can find self-similar scenes and sometimes doppelganger and duplicated objects, and we see that in Mergesort as well. We see many instances of the sorting procedure created through the recursion, and also many copies of the original deck, not exactly the same, but similar to the original one. And then finally, there's this issue of paradoxes. So any time travel story must be very careful to be consistent. You probably know the grandfather paradox, right? Where you go back in time to kill your grandfather, which makes your own existence impossible, and also the fact that you could go back in time and kill your grandfather. So any time travel story or any time travel is logically possible only if the actions performed in the past are consistent with the state in the present. Well, and the same is true for recursive algorithms. If you have a recursive algorithm and its execution leads to a finite sequence of instructions that terminate with a result, then it's fine. But if you have algorithms that, for example, do not terminate, then this amounts to a paradox. So I actually wish I had a time machine available, could go back 20 minutes and talk more about recursion. But instead, let's move on to limitations of algorithms in computing. We have already seen that sometimes the runtime makes an algorithm unusable. And this is particularly true for algorithms that have exponential runtime. So I'll give you just one example here, one sense of what that means is, suppose your input is of size 30. If you execute a linear, quadratic, or even exponential runtime, you won't notice the runtime. It's finished in an instant. If you increase the input size to 100, while the linear and quadratic algorithms still are finished in an instant, the exponential algorithm takes 9 times the age of the universe. So this is clearly too long. And it shows that exponential algorithms are really not very useful because they only work for small inputs. Unfortunately, there are many optimization problems, such as a traveling salesman problem, finding a round trip among a set of cities, or optimal packing of a box or a car. All these problems are of the sort that allow only exponential algorithms, at least at this point. And so, in this case, we see this limitation, and we have to make do with approximation algorithms. But it gets actually worse. There are problems for which there is no algorithm that cannot be solved by an algorithm. One example is the so-called halting problem, which was invented by Alan Turing in the 1930s. And you remember the Hansel and Gretel algorithms. The first two were not terminating. The third one was terminating. And, well, since termination is such an important property of algorithms, it would be great if we could define another algorithm that could look at algorithms and decide, this one terminates, this one doesn't. That would be really good if we knew this in advance. Well, unfortunately, this is impossible to do. And there are many other problems that are unsolvable. Now, algorithms should terminate, and so should presentations. So let me close with just one thought regarding the story I told you at the beginning. It so happens that I'm scheduled to have some shoulder surgery later this month, and I just hope that the algorithm terminates and that it terminates with the correct result. Thank you.